So Mr. CB, electricity basics. So this is the agenda that we have. First we will try to understand the basic terms which are used in electricity. So for example, potential difference, EMF. We won't go into much of details in understanding the difference, but we'll just skip through the definitions, the basic understanding of these quantities. So potential difference and EMF. Mr. CB, what is the potential difference or EMF?
The potential is basically the difference in the.
Yeah.
It's basically like water flowing from a higher point to a lower point. So if water is at if the height of the cliff is constant, so water won't flow. But if it is sloped, like given the diagram on straight, so water will flow from a higher point to a lower point. Similarly, in potential difference, you have current which is going from a higher potential to a lower potential.
So if we take a very basic definition to understand what exactly is potential. So for example, if I have a mountain and there are two people, one is standing at A and the other is standing at point B. Now there would be a difference in potential between these two people. Of course, the potential difference is due to the reason that this person, the person B, has put in some energy to reach point B, and this person A is, let us assume, standing on the ground only. Now because he is standing on the ground only, we can safely assume that he hasn't much. The energy, because he is standing at point A and this guy is standing at point B, he would have put less energy and this guy would have put more energy. Mr. Sivang, do we agree?
Yes, sir.
So one thing that I want to tell you guys before we start going, because I'll require the same thing, the potential, work, energy, to understand this formula, that potential difference is work done per unit charge. So that is why current and resistance are easier to understand, but potential difference, EMF, is a bit difficult. So that is why we are going into this analogy. So this person A has put in less energy and the person B has put in more energy, and due to the more energy put by the person B, he is at a higher potential. This guy is at higher potential and this guy is at lower potential. Mr. Sivang, any doubt?
No doubt.
Another thing that we can understand is, another example that we can take to understand is, let us assume that this is a building, and in this building there are, let us assume there are 3 people standing on different floors of the building, and let us assume, Mr. Sivang, you are standing here. So Mr. Sivang, which person, if he falls on you, will cause the maximum damage if he falls on you?
So the person on the third floor, C.
This guy would cause the maximum damage if he falls on you. Why is it so?
Because he's at the highest potential.
He is at the highest potential, high potential. This is at, let us say, medium potential. This is at lowest potential. Actually, you are at the lowest potential. So the difference, can we safely assume that this person would have done some work, guy would have done more work, and this guy would have done the maximum work? Mr. Sivang, do we agree?
Yes, sir.
So what I'm trying to do is, I'm trying to develop a understanding between potential of a body and work that it can do. So this person, if he falls on you, person C, if he falls on you, he will be able to do the maximum work, and this person A, if he falls on you, he will be doing the lowest work among this and this. Mr. Satya, is it making sense or not? Of course, another part of the story is that if we don't take these examples, examples in terms of people or bodies, let us say we take this example in terms of charges. So for example, I have a charge, I have charge here, I have charge here, I have charge here. Now what I'm trying to build up is that, if there is a sort of let us say there is a sort of engine. Let us say this is a sort of engine which is able to put this charge at this potential, this charge at this potential, this charge at this potential, and this charge at this potential. Mr. Sivang, is it making sense or not?
Yes, sir.
So Mr. Sivang, can you tell me what is that engine called? What is this engine called?
It's a motor.
So this engine is basically a cell like this which you use at home. Mr. Satya, have you ever seen this cell? Ever ready? Have you ever seen this? Ever ready?
So the red color.
Color cell. Mr. Satya, yes sir. So these are the kind of cells that you put in your watch. These are the kind of cells you put in your remote. So Mr. Sivang, what are we trying to say? Why do we require cells?
We require cells to apply energy
And what will yeah,
that
what?
energy will help the electrons to flow throughout the circuit.
Shabash, shabash. So for example, if you have this Duracell, what will this Duracell do, Mr. Sibam?
This Duracell will do some work in the
Shabash,
sense.
shabash,
Yes.
shabash. Mr. Satya, any doubt? So basically what a Duracell will do is, it will push electrons. Do we agree to this, Mr. CB?
Yes.
So basically this Duracell is the guy who is responsible for this potential, the potential difference, or the EMF. Mr. Satya, any doubt?
No doubt.
Now, yeah. Now there is a difference between there is a difference between potential difference and EMF, and there is a difference between these two terms. Of course, we'll do that not in this lecture. In the later lectures, we'll understand what is the difference between these two. But now in this lecture, I just want to give you a feel of what exactly is a EMF. What exactly is a potential? So potential is something which is provided by, so this. So this would be potential 1, this would be potential 2, this would be potential 3, this would be potential 4, and the difference between these two would be the potential difference. So basically what we can say is that a Duracell is responsible for providing potential difference between two charges. Can we say this, Mr. Sibam?
Yes, sir. Yes, sir.
Or if you find all of this very confusing, that potential difference, EMF, the very simple definition of a cell is that it provides energy to the circuit so that charge can flow. So basically, if your Duracell, when you say that my cell is weak, or when you say that this cell is not working, basically what you are trying to say is that that cell is not able to provide energy in the circuit, and that is why you have to change the cell, and that is why your mother or your dad will say कि यार मार्केट में जाके नया Duracell ले आओ या नया सेल ले आओ, buy a new cell. Mr. Satya, any doubt till here? So basically what we are trying to understand is that the basic function of a cell is to provide the potential or the potential difference in the in a circuit. Second is current. We understand what is current. Current is basically okay. First we'll have a look at the definition of current. The definition of current is charge per unit time. So let us try to understand this. What is charge per unit time? So for example, this is a wire, and let us assume that current is flowing, charge is moving. These are charges. The charges are flowing, and let us assume that you are standing here. So this is a common circular wire that you see at homes. This is how it looks like. So when you look, these are the charges which are flowing through the wire. Mr. Sibang, any doubt till here?
No doubt.
So basically what is current? Current is the number of charges that will cross like this per unit time. So for example, if you have a stopwatch and you start measuring the number of charges which are flowing on the right side, so the current would be number of charges passing through this particular point per unit time. Mr. Satya, any doubt till here?
No doubt.
No, sir. So current is represented by the flow of charges in a circuit. This is what I have drawn here. Then the third definition, the third quantity that we need to understand is resistance. So what is resistance? Resistance is, now if we zoom what exactly is happening here, basically whenever there is a flow, for example there is a friction, What is friction? So this is a table, and let us assume there is a book lying on the table. You try to push this book will face some friction being given by the table. So similarly, when charge is flowing through a wire, it faces some resistance, or it faces some friction. This resistance is symbol is this, and the unit of resistance is ohm. And usually in our questions I will be using R to signify resistance. So resistance can be 5 ohm, or it can be 7 ohm, or it can be 8 ohm. So this is the representation of resistance. Mr. Satya, any doubt? Another thing that you need to understand is that charge, the unit of charge is coulomb. So we know that one electron has a charge of 1.6 into 10 is or minus 19 coulomb. This is the charge on each of this electron. Mr. Satya, any doubt till here?
No doubt.
Mr. Satya? No. Okay. And Satya, what you need to understand is, yeah, this is what I was saying, the symbol of resistance. Usually in circuits, they will draw this kind of crooked wire. This is a symbol of resistance. So this resistance is not all, see, in practical life, any bulb or any fan or anything which is there in circuit, anything which is any electronic instrument in your house is a circuit. So for example, your microwave is any electronic device in your house is a resistance, is a form of resistance. So because when the current flows through it, let us assume that this current passes through this microwave, the electronic circuitry in that microwave will provide resistance to the flow of current through it. Similarly, when current is flowing through the fan circuitry, electrical circuitry will provide resistance to the flow of charge. Similarly, for if you have bulb, then basically what I'm trying to say is that any electronic or electrical instrument will try to provide friction to the flow of charge through it, and that is what is called resistance. Mr. Satya, any doubt till here?
No doubt.
So I'm not going through the bookish definitions. In very layman's terms, I'm trying to define the things, and this is the formula I was talking about, that current is this I, the symbol I. Whenever I am drawing I, basically it means current. Current is measured in amperes. So whenever I write I, basically it is current. So this is the first basic formula that you'll have to remember, that I is equal to Q by T. Charge flowing per unit time. T in this chapter would be time. So, okay. So I hope we are now able to understand what is potential, what is current, what is resistance, what is charge. Now there is a subtle difference between potential and potential difference also. Again, I won't be going into the detail. Just remember that V is the symbol of whatever your teacher might call it potential. She might call it potential difference also. Potential difference is actually the right word. So we'll call, whenever we say V, it means potential difference, but at times you will hear me saying it potential also. So it is one and the same thing. And for our purposes, we'll have to remember another word which is used in electricity is EMF. EMF full form is electromotive force. But here also there is a bit of a confusion, that though it is said electromotive force, it is spoken as electromotive force, but it is not a force, it is actually potential. And potential difference, EMF, all of them have the unit as volt. Mr. Satya, any doubt? Mr. Sibang, any doubt, or is it too much information?
No doubt.
Mr. Satya, any doubt? So whenever in your book you find potential or potential difference or EMF, you can assume it to be one and the same thing, unless and until they are asking you the difference between EMF and potential difference. Then of course you'll have to understand the difference. But for our purposes, we can assume all of these to be the same. No harm done. In one of the lectures we'll understand what exactly is the difference, but not in this lecture. So I is current, R is resistance, Q is charge. Okay. Now few more things that you need to understand is, because we are discussing all these things, the current in a circuit is measured in ammeter, and we have not discussed as yet, but once we discuss we'll come back. Now you can just listen to what I'm saying, that ammeter is always put in series in a circuit, and the way you measure the voltage difference is by voltmeter, and voltmeter is put in parallel in a circuit. So if it is getting confusing, all that you need to remember is the current is measured in ammeters by the help of ammeter. The voltage is measured by the help of voltmeter. These are the symbols. These are the symbols that you will see in circuits. Whenever you see, okay, let me actually show you a circuit, because I haven't shown you a circuit till time. So these are the worksheets that you will be doing. I'll just show you a circuit before we go ahead. So Mr. Satya, see, this is what I'm trying to tell you, that actually this is the wrong circuit, but let me show you. This might add to the confusion, so let me show you a better circuit. Okay, one second. Actually in that question they were asking you what were the errors in the circuit that was drawn, so that is why I skipped discussing that. But I'll show you a correct basically in this question they are asking you the errors. But typically this is what you can do in the laboratory. So you'll have a battery. This is direct current. What is the meaning of direct current? The meaning of direct current is that it flows from positive end to the negative end, and this is called conventional current. Mr. Sibang, any doubt?
No doubt.
Because in one of the lectures before we have discussed what is the difference between the conventional current and the actual current. Mr. Sibang, do you remember?
Yes, sir.
This is the, if these are electrons and they are moving towards this side, actually the conventional current flows in this side. Mr. Sibang, do you remember?
Yes, sir.
But again, let us not add to the confusion. So this is how a circuit in a laboratory will look like, in your physics laboratory will look like. So this is a cell. This is a symbol of a cell. This is a symbol of cell, and this is a symbol of a battery. Mr. Satya, any doubt? Now this is what I was telling you, that these lamps can be symbolized by resistances. Mr. Sibang, any doubt?
No.
Mr. Satya, any doubt? So, for example, if they show you, so for example, use standard circuit symbols in your diagram. So for example, if I had to draw a circuit symbol for this, this is how I would have drawn this. This is resistance 1, this is resistance 2, this is resistance 3, and this is my cell or battery. This is resistance 1, resistance 2, resistance 3. And just remember that if they say that all these lamps are identical, see, they have written that the lamps are identical, so what you will find is that the resistances of the 3 lamps would be the same. Mr. Sibang, is it making sense or you are getting confused?
No, sir, it's making sense.
Mr. Satya. Actually, I wanted to show you those voltmeters and ammeters. Just hold for a second. Yeah. So this is how, okay, now this is the best example. So for example, if you look at this circuit, this is a voltmeter and this is the ammeter, and that is what I was trying to tell you. So this is a symbol of resistance, or they might put a box like this. This is one and the same thing. Satya, any doubt? So if you are in one of the Indian boards, they put symbols like this, and in international board they just show you a box like this and they mark it as resistance. So this is the resistance. Mr. Sibang, any doubt till here?
No.
Okay, so these are the, okay, so for example, if they show you a symbol like this, so what if we have to read this, how will we read this? This is a resistance, this is the voltage, and this is the ammeter which measures the current, and this 3A is basically 3 ampere of current flowing through this arm. Satya, any doubt? No, sir. Okay, so for example, let me read this for you. So this is the voltage which is measured by this voltmeter. This is the resistance of this resistor, and this is the ammeter. This is how you have to do this. This is how you have to read this, because we'll be doing the numericals from this. Let me show you some more circuits. We'll be doing all these questions, Satya, don't worry. So for example, I just want to, before we start, I want to show you the actual problems. So for example, this is a lamp. This is a lamp, and this lamp is basically our circuit, is basically our resistance. Mr. Satya, any doubt? This is a rheostat. What is a rheostat? We'll just discuss in a minute. This is a rheostat. This is a cell. This is an ammeter. Mr. Sibang, any doubt?
No.
They call this as a buzzer, but we can say this to be a resistance. So this is a resistance, this is also a resistance, because these are electrical instruments which will provide resistance in the circuit. Mr. Satya, is it making sense or not? Mr. Satya, is it making sense or not? This is a ammeter, this is a voltmeter, this is a resistance, this is a resistance, this is a lamp, this is a lamp. All these are basically, so basically what I'm trying to tell you guys is that if you see this, these are basically resistances. This is a resistance, this is a resistance, this is a resistance. These two can be read like this. This is a resistance, this is a resistance, this is a resistance. So these two are resistances. CP, any doubt?
No.
Again, using my symbols, I will draw this as one resistance, and a voltmeter. So let me show you. This one is this. This one is this. This one is this. Mr. Satya, have we understood this?
Yes.
Yes, sir. Great. So, because in the next lecture we'll be discussing all this, so that is why I don't want you to get confused. Okay. So we are okay with the ammeter and voltmeter. Okay. Then let us move on to the rheostat. What is a rheostat? Basically, a rheostat. Again, in one of the lectures, we'll understand in detail how does a rheostat work. But for us, what we need to understand is what a rheostat does is we change the resistance of a rheostat. Now, when we change the resistance of the rheostat, the consequence of that is it changes the current. So, in short, what you can remember is, without getting confused, the purpose of a rheostat is to change current in a circuit. Mr. Sivang, any doubt?
No doubt.
And this is how, this is a symbol of rheostat, this is also a symbol of rheostat, and that is why I showed you that that circuit in the book where you can see a rheostat. So, Mr. Satya, is it making sense? Yes, sir. Great. So let me show you that symbol of rheostat again, so that you are able to connect the things properly. 1 second. Yeah. So this is a symbol of a rheostat. And what will a rheostat do? It will basically change the current through the wire. Mr. Satya, 1 second. So I hope we have understood everything which is mentioned in the on this page. Let us move to the second page. Now these are the basic formulas which will be used. We have discussed one of the formula. Let us go to the second formula that we had mentioned in passing, but let us go in a bit of detail. So this potential is work done per unit charge. Let us try to understand this formula, not in much detail, but in reasonable detail. So let us take the example of, let us again take this example of mountain. So for example, there is this ball which is at this end of the mountain. Now I have to move this ball up. This ball has a weight W. Now I have to move up. Because I have to move up, I have to apply some force. Let us assume that this ball I have to taken to this point. Now I'll be applying force so that it moves from point A to point B. Because I will be applying force, I'll be doing work on this ball, or let us say I'll be providing energy to the ball so that it moves from point A to point B. Mr. Sivang, is it making sense?
Yes.
Because this ball has a weight weight W, and we know that weight is given by mass of the ball into G. Mr. CB, any doubt here?
No doubt.
Now another way of understanding the same thing is, because we are doing electricity, we are not doing mechanics. Another way of understanding the same thing is, the logic remains the same. It doesn't vary much. Another way of understanding the same thing is, so for example, if this is a mountain, or let us say this is charge at point A, and I have to move this charge to a higher potential at point B. Mr. Satya, is it making sense or not? When I have to move from point A to point B, of what do I have to move? I have to move this charge. I'll have to do some work on it, or I'll have to provide energy to it. And this charge, let me mark this charge as Q. So the potential or the potential difference is the amount of work that is required to move a certain charge from point A to point B. Mr. Sivang, is it making sense or not?
Yes.
And who provides this energy, Mr. Sivang?
So the cell.
The cell provides the energy. Mr. Satya, is it making sense or not? So when I say, so let me draw a very, very simple diagram. This is called a key. This is a cell. This is a resistance. The conventional current flows from positive end of the cell to the negative cell. Now what I'm trying to tell you is that this resistance is, you can imagine this resistance to be a sort of mountain, where this point is point A, this point is point B, and using the energy of the cell, we are able to move the charge from point A to point B. Mr. Sivang, is it making sense?
Yes, sir.
So of course B is at higher potential and A is at lower potential. Mr. Satya, yes sir, no sir?
Yes, sir.
So this can be assumed to be the point A, this to be point B of a imaginary mountain. And what is the purpose of the cell? The purpose of the cell is to move charges up the mountain, up the potential. So is it making sense? And that is why we write the definition as, the complete definition is written as the potential difference between point A and B. That is usually how they write it. VB minus VA is work done in moving charge from A to B, where Q is the charge moved. This difference can be written as a delta V. This work AB can be simply written as W upon Q, and that is why this delta V is the potential difference. And at times even this is not written. Even this is not written. They simply write this as V is equal to W upon Q. Mr. Sivang, is it?
Yes, sir.
Is it making sense, Mr. Satya? Is it making sense or not? Yes, sir. So this is, or if you don't want to understand all this nonsense, you simply say that voltage is equal to work upon charge. But this is one of the very important definitions in electricity. You can't afford to ignore this definition. This is one of the fundamental definitions. It is as important as this, that current is equal to charge upon time. Okay. The third very basic definition, very basic formula which is used in electricity is Ohm's law, which is called V is equal to I into R. Now, V is equal to I into R says that so let us take this circuit only. So V is equal to IR says that if this is the voltage and the current flowing is I and the resistance is R, the relation between these three quantities is given by this, and this is what is called Ohm's law. Mr. Sivang, any doubt? Mr. Satya, any doubt?
No, no.
Mr. Satya, no sir. Okay. Now, another thing that you can understand is that, again, I won't be going into detail in this lecture. Not all the materials will follow the Ohm's law. Also, there will be materials which will follow Ohm's law in certain quantities. That is, in certain areas they will follow Ohm's law, but in other areas they won't follow Ohm's law. So that is why you'll have two kind of materials. One are called ohmic materials, the other are called non-ohmic materials. I am not going into the detail, but all I am trying to tell you is that not every material in this universe follows Ohm's law, and materials follow Ohm's law in certain, let us say to simplify the things, in certain temperature intervals. So for example, there would be a material which will follow Ohm's law between say 30 degrees Celsius to 150 degrees Celsius. Beyond that, it won't follow. Mr. Sivang, is it making sense or not?
Yes.
Mr. Satya, is it making sense or not? Yes. Okay. So we have understood this. Okay. Now, before I go on to discuss so we'll have to understand. We'll go through the basic of understanding what is series, what is parallel. We'll do that, but before we do that, I will spend some time to build on this. See, this is one of the advanced formulas, so no use. It won't be used much, Mr. Satya, but we'll spend few minutes discussing this. This is one of the advanced formulas, so don't worry. But we discussed here that V is equal to W by Q. V is equal to, this is the formula we derived. V is equal to W by Q. Therefore, I can write W as V into Q. Mr. CP, yes or no?
Yep.
So W is equal to V into Q. I can cross multiply these two. So if W is equal to V into Q, then W is equal to V upon Q. What I can do is divide both sides of the equation. Divide both sides of the equation by T. Mr. Satya. Yes sir, no sir. So
Yes.
Divide left and right side by T. So this will be W upon T. This would be VQ upon T. Now just remember that Q upon T can be written as I. So my right side becomes V into I, and my left side is work upon time, which is actually called power. Mr. Sivang, yes sir, no sir.
Yes.
So another formula which is used, Mr. Satya, you don't need to worry about this. You won't be using this in this year. but Mr. Sivang would require this. So Mr. Sivang, this is the formula which we need to remember, that power is equal to V into Y. Have you understood, Sivang, how to derive?
Yes, sir. Yes.
Again, I'm repeating again and again that W is equal to VQ or V is equal to W by Q is an important formula. Now using this formula, we will be deriving power is equal to VI. We will be using power is equal to VI, which is an advanced formula to understand the heating effects of current, Mr. Sivang. We'll be using this to understand the heating effect of current. So for us, this would become very, very important. Satya, you don't need to worry about this. Satya, Siri, are we clear about this?
Yes, sir.
So the symbols which are used are work, the unit is joule, another symbol we used was voltage, symbol is volt, charge is coulomb, we used time in seconds, we used current which is an ampere, we used power with whose unit is watt. Mr. CB, any doubt here?
No.
Okay, so we are clear with page number 1, we are clear with page number 2, the left part of this page is clear. So V is equal to IR, I is equal to Q by T, V is equal to W by Q. I'm repeating this again, not all material follow Ohm's law. Just remember this, this might be one of the questions, one of the trick questions they might ask. Not all materials follow Ohm's law. There are two kinds of materials, there are ohmic materials and then there are non-ohmic materials. There are very important questions which are asked on this fact. Okay, now let's move on to the series and parallel circuits. Now series and parallel circuits, we will need to, in the next lecture we will be solving questions from series and parallel circuits, but just to start the discussion so that we are able to do more questions in the next lecture, just to start the discussion, there are two kind of circuits which are drawn in electricity, fundamental circuits which are drawn. So one is drawn like this, this is one resistance, this is another resistance, this is a cell and there is a key. See, the only key is something which is used for on off. It is basically a switch, nothing complicated, it is just a switch. So that is the only purpose of a key. In most of the diagrams I don't even draw a key, but that is understood. So this is my cell, this is my resistance 1, this is my resistance 2. So have you understood this circuit? This is what is called a series circuit. We'll be doing more tomorrow we'll be doing more questions regarding this series and circuit diagrams, so don't worry. But just to start the discussion, this is called a series circuit. Now, what you need to remember about series circuit, there is only one thing that very important thing that you need to understand about series circuit is that this is the positive charge, this is the negative charge. The same current will flow from resistance 1 as well as resistance 2. Basically, what I'm trying to tell you is that current behaves like water, So you can imagine water flowing through this pipe. So the same water will flow through R1 as well as R2. If you remember this fact, your life is very sorted. As Mr. Satya, any doubt? So whenever you are confused about a series circuit, just remember we'll be discussing formulas also, we'll be discussing numericals also. But as long as you remember this simple fact that current behaves like water in series circuit, the same water, I'll mention it here. Same amount of water flows through both resistances. As a matter of fact, if there were 3 resistances, let us assume that there are 3 resistances. This is how another resistance look like. So all these 3 resistances, R1, R2, R3, same amount of current will be flowing through them. Mr. CB, any doubt?
No doubt.
So this is what I mean when I say that what is a series circuit. So if you see this circuit, current I is coming out of the we can say that the current I is coming out of the cell. The same current flows through this resistance as well as this resistance. Mr. Satya, any doubt till here?
No.
Now there are formulas we'll discuss in the next lecture. We won't go into detail. So one of the formula is V is equal to V1 plus V2, another is R is equal to R1 plus R2. I don't want to discuss it in this lecture, but these are the fundamental formulas that are used in series circuit. Okay, the other kind of circuit which we use in electricity are called parallel circuits. Now in parallel circuits, again we take the analogy of electricity because that is the best analogy to understand the circuits. So this is one of the resistances, this is the second resistance. You have a cell here. Just remember that if the these two resistances, the first thing that I am saying is that R1 and R2, they are different resistances. Now if current I starts from cell 1, it will get bifurcated here like water. Current I will flow through R1, current I2 will flow through R2, such that I is equal to I1 plus I2. All this equation means is that because current is flowing like water, if I current starts from this cell, once it reaches this point, some of the water will go this side, some of the water will go this side. Again, I1 will be flowing through this, I1 will be flowing through this, I2 will be flowing through this. At this point, let me call this point A, let me call this point B. At point B, this I1 and I2 will join together so that I flows back. So that is why if you look here, what you will understand is that the total current in the system has to be the same. Mr. Satya, any doubt? Mr. CB, any doubt?
No doubt.
So I is equal to I1 plus I2. I don't want to complicate the matters much, but if we assume that the resistances are same, so for example, this resistance and this resistance, they are same, then if I flows through this, same I and same I will flow through this as well as through this. Any doubt?
No doubt.
So Mr. CB, can you tell me what will be the value of I here?
So it will get divided.
Okay, so what will be the value?
I1, we could assume it to be I1.
No. Can you tell me in terms of I, how much will it flow through this? How much through this? In terms of
Half, I upon 2.
I upon 2. So any doubt? Now this is the same like saying that I have 3 equal resistances. I have R, R, R. Now I have 3 legs, and from the cell I water starts flowing. So how much, Mr. CB, water will flow through each of the resistance?
I upon 3, I upon 3, I upon.
Mr. Satya, any doubt? Now here, this is one of the basic formulas that you'll have to remember, that current will get divided. And in series, you need to remember that the same current will flow through this, through this, through this, and which will be equal to this current which starts here. Same current is flowing. So this is, again in the next lecture we will be discussing these formulas. I won't be discussing the formulas in this lecture. Then let us move to the final formula of this lecture. Again, this is one of the advanced formulas, Satya. You don't have to worry much about this. This is only meant for Mr. Sivan. So resistance can be mentioned as rho L by A, where rho is called the resistivity of the wire. Any wire. So for example, if this is a copper wire, it would have some resistivity. If it is a silver wire, it would have some other resistivity. If this is a, let us say, carbon electrode, it has some resistivity. If it is a silicon, the substance is silicon, it has some other resistivity. L is the length of the wire, this length. And A is the area of cross section. What is the area of cross section? Area of cross section is, if I look at this wire from this end, then I will see a circle like this. This is called the area of cross section. So this is another important formula, another basic formula that is studied. Mr. Sibang, any doubt?
No doubt.
So again, as mentioned, Satya, we won't be using this formula, R is equal to rho L by A. We won't be using this formula. We won't be using W is equal to V by Q. But we'll be using series, parallel. We'll be doing a lot of questions from series and parallel in the next lecture. And for that, we'll be using all these terms that we have discussed in this lecture: current, resistance, charge.